yesterday's class, we were discussing about the basics of digital communication, or what is the interface between analog to digital, in the sense how to convert a given analog signal to digital. And the first and foremost step in that is sampling. So we have to sample a given analog signal, then we would be able to convert it to digital by adding one more step, that is quantization. So sampling and quantization are two fundamental steps involved in converting any analog signal to a digital signal. And I was showing you yesterday what is sampling. As you can see here, sampling involves converting an analog waveform into a discretized time waveform. In the sense, the time axis will be discrete. So if I have one sample of the analog signal like this at time ts, I can take the second sample at time 2 ts, third sample at time 3 ts, so on. So converting a given analog waveform into a discrete waveform which is discretized only in the time axis. Whereas in terms of amplitude, it is not discretized. It will have all values. As I was telling you, the value here can be 1.1, the value here can be 2.3, here it can be 2.2, whatever. So you can have all sorts of amplitude values possible depending on the time when the sample has been taken. But in the x-axis, I can have only, excuse me, in the x-axis, I can have only fixed samples. That is fixed times. I can have time ts, 2 ts, 3 ts, like that. Ts represents the sampling time period or the sampling interval. Okay. So we can take samples either using impulses like this. When I multiply a given analog signal with a periodic impulse train, I'll get samples with impulses like this. Or if I use a periodic pulse train instead of impulse. Remember, impulse train is the ideal case. It is very difficult for us to generate impulses in practice. Okay. So usually we can generate only pulses rather than impulses. Therefore, we usually will have a periodic pulse train to take samples. Naturally, we'll be multiplying the given signal with a periodic pulse train, and you will get the samples in this form, the one which we have written on top. Okay. So such a condition, such a sampling is called as pulse amplitude modulation, or PAM. We call this as PAM, pulse amplitude modulation, where we have varied the amplitude of the carrier pulse. Yeah. Any doubts? We have varied the amplitude of the carrier pulses in accordance with the amplitude of the message signal. So you have the message signal here. The carrier pulse amplitude, the amplitude of the pulses is changed in accordance with the message. We call this as pulse amplitude modulation. But initially, let's consider ideal sampling. When we use impulses to sample, we call this as ideal sampling. And when we use pulses to sample, we call this as practical sampling. So practically, it is possible for us to generate only pulses and not impulses. Okay. So whenever we use impulses to sample, it is ideal. But whenever you use pulses, it is practical, or pulse amplitude modulation. Then, considering this sampling process, we also wrote the statement. Anyway, sampling converts analog into corresponding sequence of samples which are distributed in time. Proper selection of the sampling rate is very important, because that is what determines how uniquely the samples will represent the original signal. So at the receiver, whether the given samples represent the original signal correctly or not, that is determined by the sampling rate. Remember that. Our sampling theorem also states the same thing. So it is determined by the sampling theorem. And for the sampling theorem, we are considering the input signal as g of t, sampling time or time period as ts. Ts is 1 by fs. And we'll call the set of samples which are spaced ts seconds apart. That g of nts, we'll come to it later. We'll be using it. Ts is referred as the sampling period, which is 1 by fs. And let g delta of t be the what? The product of the given signal g of t with the impulse train gi of t. So when I multiply g of t with impulse train gi of t, whatever result I get, that we are calling as g delta of t. Okay. Now, the sampling process is indicated here. Let's define the sampling theorem. According to sampling theorem, a band-limited signal having no spectral components above FM or W. Its frequency should be, highest component should be less than W or FM. FM if it is a single tone, okay? It can be sampled uniformly at intervals of TS, which is also 1 by Fs. Then it can be transmitted over the channel and recovered completely at the receiver by using values of these samples. Whatever samples we have taken and transmitted from the transmitting side, we can recover them correctly at the receiver by using these samples only if, remember the most important condition here, only if the sampling interval is approximately 1 by 2 FM or 1 by 2W, greater than or equal to that. Or in other words, the sampling frequency Fs should be greater than or equal to 2W or 2FM. Only if this condition is satisfied, proper recovery of the original message, this kind of message from the samples is possible. Remember, it is these samples which we are going to send, these impulses. Okay, since you're going to send these impulses, how you get back this complete analog or continuous signal at the receiver is based on the sampling rate. You should sample at a frequency which is always greater than or at least equal to that of twice the message bandwidth. Please remember that. This is called sampling theorem. Okay. So you can sample, you can transmit and recover only if Fs is greater than 2W or 2FM. And we spoke of basic equations in the time and frequency domain. One form of the basic equations. G of t is shown here. Gi of t, the impulse response, can be represented as summation of shifted impulses. Summation n is equal to minus infinity to plus infinity delta t minus nts. We wrote this. Then we said when we multiply the two, we'll get the sampled signal g delta of t. That is given as g of t into this impulse train. And now let's shift to frequency domain to check out what is g delta of f. G of t gets converted to g of f. Product becomes convolution, and the Fourier transform of this impulse train in the time domain, the Fourier transform in this frequency domain becomes delta f minus n fs divided by ts, or 1 by ts. 1 by ts is nothing but fs. We can write it like this also. G delta of f can be written as fs summation n is equal to minus infinity to plus infinity g of f minus nfs. And in the frequency domain, you see how the spectra look. The initial message spectra is a triangular spectra g of f as shown. And the spectra of the impulse train is another impulse train which is distributed at multiples of Fs. Impulses at Fs, 2Fs, 3Fs, at all multiples of Fs, I'm going to have impulses. And finally, the sampled signal G delta of F will be the basic triangular signal existing at all points where the impulse has existed. And how do we get this? We get this using the sifting or sampling property, which tells the convolution of any given signal with an impulse will be that signal existing wherever the impulse exists. So this G of F convolved with this impulse train becomes G of F minus NFS. And this is how the waveforms look. I hope it's clear till here. If you have any doubts, please ask. Okay, if you don't have any doubts, let's continue. So as I was telling you, whatever we are discussing with impulses, it is called ideal sampling. We can write this ideally sampled signal equation in a slightly different form known as through this equation. So the G delta of T, which we wrote in the last expression, we wrote G delta of T as what? We wrote G delta of T as what did we write? It was in the previous
Gi of T into
G of T into summation.
G of T into G. Okay, that into impulse.
Yes. This was one expression which we wrote for G delta of T in the previous case, right? Now we can represent this in a slightly different form by taking this product in this form. Here, this G of T multiplied with this, we had left it like this only at this point. Here, what we are doing, we are taking this G of T inside the summation. So I will replace this T with NTS and I'll say this G of NTS represents the weights or the amplitudes of each of these impulses. So this G of NTS is nothing. Remember how the signal looks? See, the signal is something like this and I'm going to have impulses like this. Yes or no? Each of the shifted impulses, each of them represents a shifted impulse, delta T minus NTS. Each of them will have some amplitude. That amplitude depends on the given signal G of T. So what I am taking here is G of NTS, where G of NTS will represent the amplitude or the scaling factor or the weighing factor for each of the impulse. So delta T minus NTS represents every impulse. The amplitude of that impulse is given like this. We can write it like this, yes or no? Every impulse is scaled to a different value and that value depends on the given function G of T. So this is an alternate representation for the ideally sampled signal where we sample a given message using an impulse train. Okay. Remember this equation also we'll use commonly. So as the idealized delta function has unit area, the multiplication factor G of NTS can be considered as the mass or weight assigned to the impulse, as I was telling you now. And a delta function which is weighted in this manner, it's approximated by a rectangular pulse of duration delta t and amplitude G of NTS by delta t. See, whenever you have a weighted impulse, remember impulses are difficult to generate. I can represent each impulse with a small pulse and this pulse will have time duration delta t and it will have an amplitude G of NTS by delta t or amplitude G of NTS time duration delta t. Each impulse will always be a pulse of very short duration. That duration delta t which we are taking should be very, very small. Okay. This is how we call the weighted impulses. One thing you remember, if I divide this with a very small time duration, naturally this magnitude becomes higher. The area under the curve should be what? Area under an impulse should always be 1, right? So remember, that's the property of the impulse. Area under the impulse should always be 1. So even if I'm using a small pulse, practically remember there is nothing like impulse. You'll have a very short duration pulse instead of impulse. That's what you can generate practically. The shorter the time duration of the pulse generated, the more closer it is to an impulse. So the shorter the time duration means the higher its amplitude should be. That's why we take G of NTS by delta T, because that indicates a very high magnitude. The smaller the delta T, the higher or larger the value of the amplitude G of NTS. Okay. So remember this representation also, we'll use this more commonly. Knowing that the uniform sampling of continuous time signal of finite energy results in a periodic spectrum with period equal to the sampling rate. So we can use the, we have already derived that, the Fourier transform of G delta of t. G delta of t, whatever we had, its Fourier transform would be, we got this expression here, right? Here, G delta of f is Fs summation G of f minus nfs. The same thing we are writing. The Fourier transform of G delta of t can be expressed in this form. Okay. N or M, anything you can use. Here we've used M and N interchangeably. So if we now take Fourier transform on both sides of equation 3.1, do you remember which was equation 3.1? See, this was equation 3.1, the one highlighted in yellow here. The equation for G delta of t, which was written as equal to G of NTS into delta t minus NTS with summation from n ranging from minus infinity to plus infinity. So now I want to take Fourier transforms of this equation on both sides. So what is the Fourier transform of G delta of t? It becomes G delta of f. The Fourier transform of G delta of t is G delta of f. And on the right hand side, I have the summation G of NTS. And what is the Fourier transform of the impulse? How do you find the Fourier transform of this? You can observe here. So to get the Fourier transform, what should I do? I should integrate from minus infinity to plus infinity the given signal G delta of t into e to the power of minus j 2 pi ft dt. This is how I'm going to get the Fourier transform, right? The equation for Fourier transform, all of you please recollect. Finding the Fourier transform of a signal, any given signal, is multiplying the signal with e power minus j 2 pi ft and then integrating it, finding the area under the product curve. So when I substitute for G delta of t as G of NTS into delta t minus NTS, this is the substitution for G delta of t into e power minus j 2 pi ft dt. Okay. Now I'll interchange the summation and integration. I'll take the summation outside, integration inside. This becomes integral G of NTS delta t minus NTS into e power minus j 2 pi ft dt. Now summation G of NTS is a constant. We said it is a weighing factor or a constant amplitude. right? It is the amplitude or scaling factor. We'll take it outside the integral because it's a constant. It won't change with integration. So I'll bring it outside. Now I have to integrate what is delta t minus nts into e power minus j2 pi ft. How do I resolve this? Remember here, e power minus j2 pi ft is an exponential function. This exponential function is being what? Ideally speaking, the meaning of this is e power minus j2 pi ft is getting convolved with the impulse. Yes or no? Convolution is nothing but integration of the product. Yes or no? So this is a simple convolution of this given signal e power minus j2 pi ft with an impulse. Which property can I use? The shifting or sampling property. We used this even before, just now. We say that any given function, when it is convolved with an impulse, it will result in that function shifting to the point where the impulse exists. So here the impulse is existing at nts. So I'm shifting this e power minus j2 pi f to the point nts. T is replaced with nts, right? This is called the sampling property or shifting property. So we are just using this convolution operation to replace this function e power minus j2 pi ft with e power minus j2 pi f nts. We already have this g of nts outside and the summation. This is what we have considered here. So in your textbook, you'll see everything will be written directly. But for you to remember, I think it's better if you go through the derivation steps. Okay, so I hope you understood how we got g delta of f from this equation, how we could take Fourier transform of equation 1 and how it resulted in this equation. That's what I have shown you here. Okay, any doubts?
Mom, the other slide you showed, can you show that again?
This one,
Yeah. In that 3.2, how did we get that?
3.2.
2.
3.2 was from the initial, this derivation here.
Oh, okay. Okay.
This was when we considered this as g of t into summation of the impulses and we directly converted to frequency domain, then we got this. Okay,
Yeah, ma'am,
this
thank you.
is 3.2. Okay, the relations derived up to here apply to any continuous time signal g of t. I can take it as g of t, x of t, anything. Any continuous time signal of finite energy and infinite duration. Okay, energy of the signal should be finite. It can go on extending up to infinite time duration. If the signal g of t is strictly band limited, now we'll do some more additional simplification or let's say substitutions. If the signal is band limited, that means it has no components. It is something like this, right? It has no components above W. So it has all frequency components lying between 0 to W. Then the Fourier transform g of f for g of t will be 0. This is your Fourier transform g of f. It is surely 0 at all frequencies greater than W. And since I have to take negative frequencies also, I'll use modulo f. So at all frequencies greater than W, you see this function is 0. This we call as a strictly band limited signal. Now, how do we write the spectrum of this strictly band limited signal? It looks something like this. I showed you in the previous slide also. If this is g of f and let's say This represents the function at 0, g of 0. Then at every fs, it will be repeating. We saw this. Here we have considered Ts as 1 by 2w or Fs is equal to 2w. We have taken the sampling rate or the sampling frequency as exactly 2w. That's why you see these ends will touch, because this signal will range from 0 to w. This one will range from Fs minus w to Fs plus w, so on. So because we have used exactly double the message bandwidth, you see all these will touch. Initially I showed you if I choose Fs is greater than 2w, then this Fs, 2Fs and all will be a little far apart. You see a separation between these shifted spectra, right? Remember, the spectra are obtained based on the equation Fs into what? Summation delta F minus NFS, right? We wrote this as G delta of F. This was the other expression for G delta of F. That spectrum we are writing. Okay. For now, you ignore this 2WG. I will come to that a bit later. So for this, when we write the spectrum, if I choose the sampling frequency to be much greater than 2W, you have a clear separation in the spectra. But if you choose it as exactly 2W, you see the spectra will be touching each other. And we already wrote this expression for G delta of F. We have it here. G delta of F is written as G of NTS into e to the power of minus J2 pi NF TS. The what we derived just now, the same thing we have written here. Now, since the sampling period is taken as exactly 1 by 2W, let us substitute that value Ts as 1 by 2W in equation 3.3. So what do I get? Remember what was equation 3.3? G delta of F summation n is equal to minus infinity to plus infinity G of NTS into e to the power of, right? E to the power of minus J2 pi F NTS. This was equation 3.3. Now, if I substitute wherever I have Ts, I'll put 1 by 2W. This first part becomes G of n by 2W e to the power of minus J2 pi Fn. You substitute and see minus J2 pi Fn Ts. For Ts, what should I put? I should put 1 by 2W. In place of Ts, I should put 1 by 2W. 2 cancels out. So what is left? Minus J pi Fn or minus J pi Nf divided by W. Is that okay? So in this equation, wherever we have the sampling interval Ts, I am putting 1 by 2W because we are going to have a strictly band limited signal and we are sampling at a rate with, sorry. So we have the signal which is strictly band limited, and when we substitute that we know we have to sample at a minimum rate of Ts is equal to 1 by 2W. That's the lowest sampling period possible. Anything higher than that is good enough. Okay. And when I use that worst case condition, this will be the substitution. Now, equation 3.2 we use to get the Fourier transform of G delta of t. We can also write what was equation 3.2? I think equation 3.2 was G delta of F is Fs summation delta F minus MFS, right? With M is equal to minus infinity to plus infinity. Since we have N in this, we have used M here.
It is G, not the delta now, ma'am. It is G now, ma'am. G of F minus.
Sorry. G, this should be G of F minus MFS. This was equation 3.2. So we are using that. And finally, we write this expression for G delta of F as Fs into, I'm just extracting the condition when M is equal to 0. This is the condition for M is equal to 0. See, in the equation 3.2, which we have shown here, G of F
Ma'am, and
minus
3.2 is
MFS.
for G delta of T.
Pardon?
3.2 equation is for G delta of T, not G delta of F.
No, this is G delta of F only, right?
No, 3.2 is G delta of T.
1 second. No. This is G delta of T and this are the Fourier transform pairs. What we have shown here is not an equal
Okay.
to sign. It is a dual arrow indicating that they are Fourier transform pairs. So
Okay.
whatever is this, this represents G delta of F only. Okay. I think you confuse this to an equal to sign. I can't have one side in the time domain and the
Yeah.
other in frequency.
Yeah, ma'am. Thank you.
Okay. So now this G of F, I'm using the condition when M is equal to 0. I'm taking it outside separately because I want to do some more simplification with that. So from this, if I extract the condition when M is equal to 0, this becomes Fs into G of F, okay, plus whatever I have here, I'll retain as it is, plus Fs summation M is equal to minus infinity to infinity G of F minus MFS. You see here we have used the condition. I can't use M is equal to 0 here because that value I have extracted outside. Okay, it's the same equation. We have just rewritten this equation 3.2, taking out the term for M is equal to 0. When I put M is equal to 0, I'm going to get G of F here, G of F minus 0. That I have taken it out of the summation. So it's actually multiplied with Fs, everything. So Fs into G of F is the value for M is equal to 0. Plus what is remaining here is Fs summation G of F minus MFS. And you should remember, I can't use M is equal to 0 here because that has already been taken out. We call this as equation 3.5. Okay. And for the conditions specified about F, that is for condition G of F is equal to 0 for what? Whenever the given frequency is greater than W. How do I use this? From where did I get this?
Strictly band limited spectrum.
It is band limited. Please remember, we are considering a strictly band limited signal whose value exists only between minus W to plus W. So this G of F is strictly 0 for all values of F greater than or equal to W. Okay. And the sampling rate is exactly equal to 2W. We get that. So when we use this condition in the previous equation, you'll, I think in this equation here itself, we can substitute this first part. The second part becomes, let's leave it. So what do you get? G delta of F is equal to Fs into G of F. I am interested in finding G of F. G of F becomes G delta of F by Fs, and Fs we have considered as 2W. G delta of F by 2W. That's what is the substitution we have written here. See here, G of F is G delta of F by 2W. This happens because we are using a strictly band limited signal. Okay. So this is one condition. And later on, when we substitute equation 3.4 in 3.6, the equation 3.4 is given here. The value of G delta of F, which we have here. Please observe. You should substitute this in this equation, which we have written just now. What happens? G of F is equal to 1 by 2W summation. For G delta of F, I am substituting. Summation n is minus infinity to plus infinity. G of n by 2W we had got. E to the power of. So this we obtained by taking Fourier transform, the Fourier transform equation. E power minus j pi n f by W. Okay. So this is,
Ma'am,
yeah.
in getting 3.6, why did we not consider the second term, the summation term?
Because of this reason. Strictly band limited signal, no?
Yeah, but
This,
the summation term is from minus infinity to plus infinity. So some of the components might be there.
no. Usually what happens, let me say, this, what was it? G delta of F, right? So, one second. G delta of F, we had written it as what? Summation n is equal to minus infinity to plus infinity. G of n by 2W, right? G of n by 2W e to the power of minus j pi n f. Yeah,
Yes, ma'am.
pi
Pi n f
n
by
f by W. Now, when we have a strictly band limited signal, okay, in the other expression also, we had an alternate expression for G delta of F, where we used Fs summation m is equal to minus infinity to plus infinity. What? G of F minus mfs, right?
plus fs. Okay, yeah, yeah.
F minus mfs. We have taken m as the variable here. If I have a strictly band limited signal, this equation, the second equation, I can put Fs as 2W, and the summation m is equal to minus infinity to plus infinity. G of F minus m into 2W. Okay. Wherever I have Fs, I am substituting 2W. And in this, if m is equal to, sorry, if m is equal to 0, what happens? What will I get G delta of F as?
G of
2W
into G
outside
of.
into trying to do here. So when we have considered a strictly band limited signal, and when I limit that F exists only till W, then I'll get this condition. And from that, we are getting G of F as 1 by 2W G delta of F. It exists only in this range. The given G of F will exist only in this range for a strictly band limited signal. That's what we are showing using equation 3.2. Okay. So if you take
Okay,
it
ma'am.
from
Thank
this
you.
equation, I think it's easier to get that, right? Rather than considering from 3.3, if you use this equation 3.2, it would be easy to specify this. Now, as we said, substitute 3.4 in 3.6, you get this equation for G of F. Please see here, this is 3.4. G delta of F expressed in this form is 3.4, and 3.6 is the expression for G of f. So I'm just taking this substitution, this equation I'm writing for G delta of f. I'll get this. So this is let's say one step. This means that if the sample values g of n by 2w of a signal g of t are specified for every values of n, then the Fourier transform g of f of the original signal can be uniquely determined from its samples. That's the implication of this equation. This is also equation 11 is also called a discrete time Fourier transform, we call this as. Okay, and we'll be using this signal basically as one of the inputs to reconstruct, get back g of t from g of f. So here we first defined g of t, the basic message signal. Then we sampled it using an impulse train, ideal sampling. And then we got g delta of t, which was the sampled signal. Then we converted it to frequency domain to get g delta of f. And from that g delta of f, we are checking how we can get back g of f. So how to define g of f in terms of g delta of f? G delta of f is the sampled signal Fourier transform, whereas g of f is the Fourier transform of the basic given signal. Remember this. G of f is the Fourier transform of the given signal. G delta of f is the Fourier transform of the sampled signal. Here we are trying to, using the strict band limiting property, we get an expression telling that g of f can be written in terms of g delta of f divided by 2w. Okay, and from that we already have an expression for g delta of f in terms of g of n by 2w and all that. When we substitute that, this is known as the discrete time Fourier transform. And from this, what is our interpretation is, if the sample values are given by this g of n by 2w for any signal g of t. You have any signal g of t, and we are taking the sample values g of n by 2w for all n, for any n values from minus infinity to plus infinity. Then the Fourier transform of the signal g of t, that is g of f, can be uniquely determined from its samples. These are the samples. G of n by 2w are the samples. We are telling the Fourier transform can be uniquely determined from its samples. That's the actual physical interpretation. Yeah, it's written here also. So if the sample values of an analog signal are specified for all n, for all the n values between minus infinity to plus infinity, if you specify the samples, then the Fourier transform of the signal is uniquely determined using the above equation, the discrete time Fourier transform DTFT equation, equation 3.7. This is another important equation which you should remember. Everything you have to practice. And we can also conclude that because g of t is related to g of f by the inverse Fourier transform, the signal g of t is itself uniquely determined from the sample values g of n by 2w for all values of n between minus infinity to plus infinity. So if we can specify g of f using these samples g of n by 2w, then I can also get back g of t using the same samples. That's all we say. So understand in simple terms. Now we have to move towards reconstructing the signal from the samples. So you have the samples g of n by 2w. How are you going to get back g of t from these samples? We have to see. Okay. They'll ask for both reconstruction. Initial part what we did was interpolation. Now what we are doing is reconstruction. Okay. So now we have equation 3.7. We'll take that equation 3.7 and we'll substitute that in the inverse Fourier transform formula. So what was the inverse Fourier transform? How do I define? I'll get back. We had equation 3.7 for g of f, right? Please remember this equation. This is defined for g of f. From this, I'm trying to get back g of t. How will I get back g of t from g of f? What is the IFT equation? It tells you g of t is integral minus infinity to plus infinity. It should be, but we know the signal exists only between minus w to plus w. So anyhow, we have to limit it to that. The given Fourier transform of the function into e to the power of minus j 2 pi ft df. This is the expression for IFT, inverse Fourier transform of any signal g of f, right? Actually, it is minus infinity, but since the signal is limited to this band, we change it to minus w to plus w. This is what we have to find. And g of f value we have specified in equation 3.7. You substitute and simplify. I want you to try it out by the time I take attendance. Try out this
No, which is
simplification.
the equation 3.7?
Equation 3.7 is this g of f. G of f is, what did we write? 1 by 2w summation n minus infinity to plus
Using the
infinity.
samples, we don't know that one.
Yeah. G of n by 2w into e power minus j pi nf by 2w. 2 got cancelled, right? W. I think it's right. Check. This one.
Okay, thank you.
Yeah, just make a note of this. This is g of f. You should substitute. I think we have written correctly, no? Yeah. So substitute this and simplify. Do the simplification. Find what is g of t. Simplify to whatever extent possible.